So hello everyone. Today I'm going to present a CVPR 2023 paper called Diffusion Pose toward more reliable 3D pose estimation. This is one of the pioneering paper about using diffusion for pose estimation. So about the contribution first, they propose a novel framework that represents a new brand of method with diffusion of architecture for 3D pose estimation, and that can naturally handle the indeterminacy and uncertainty of 3D poses. And their model gives state-of-the-art performance on two widely used human pose estimation benchmarks, and they provide various designs to facilitate this 3D pose estimation using diffusion. So first, initialization of how they initialize the 3D pose distribution, and they use Gaussian mixture model-based forward diffusion process, and they use conditional reverse diffusion process. The overall architecture is given here. This is the architecture. This is in this figure you can see inference process. The training process is not described here. The inference process described here, and I will go details one by one about this architecture. So first of all, some background on diffusion models. Diffusion models are a class of probabilistic generative models that learn to transform noise to a sample. So, in forward diffusion, we sequentially add a little bit noise to the pose and make it noisy pose. And in reverse diffusion, we take this noisy pose and try to denoise it using a diffusion model. So if the forward diffusion is formulated as follows, but the main thing we need to focus is the one that I highlighted here. This formula, they changed this formula using Gaussian mixture models. So I will explain about this later on. So this formula basically what it does is it adds the noise to H0, which is the denoised sample that has no noise, and this alpha k is basically a fixed decreasing sequence that controls the noise scaling at each diffusion step. So let's move on. So first of all, how do they initialize the 3D pose distribution? So to initialize the distribution for X and Y values, they generated using heat maps coming from a off-the-shelf 2D pose detector. But for Z distribution, they propose two approaches. One way they can do Z distribution is to calculate the occurrence frequencies of the Z values in the training data, and then they can obtain a histogram for every joint for the Z distribution, or by just using context encoder. And they claim that using context encoder, they lead to faster convergence. The model converges faster than using histogram. This is the visualization of that process. So we have these heat maps coming from a 2D pose detector and the depth distribution, and they initialize a pose like this. And about the forwarding the pose diffusion. So that's the problem. We cannot simply diffuse a 3D pose to a standard Gaussian noise, because the initialization of this 3D pose distribution is not a random noise. It is a XYZ distribution according to the 3D pose uncertainty. Also, the random Gaussian noise will not represent every 3D pose because the 3D poses are unique in a sense, and they have complex shapes in terms of their distribution. So the solutions they come up with is to fit a Gaussian mixture model to model this uncertainty distribution, and forward diffusion poses such that the generated noisy distribution becomes equivalent of the fitted GMM distribution that we want to come. So basically the formula that I showed before, the standard formula for diffusion becomes like this, where these G's are the ones that coming from Gaussian mixture model. So this is the mean according to this Gaussian mixture model, and noise according to the Gaussian mixture model. And this is the if the noise distribution, the noisy this is the noisy representation of HK in a GMM sense. Okay, let's move on. So what about the reverse diffusion for pseudopose estimation? And they say that if they directly perform reverse diffusion, it may not be sufficient because we lose the context information. So what they come up as a solution is provide additional information to the diffusion model by extracting context information from the 2D post sequence derived from video. It can either be a 2D post sequence from a video, if it is a video, or from a frame, which is a single image. So in the end, we have this FSD, which is a special temporal information that the features, and this FKD is the unique step embedding to represent case diffusion step by the sinusoidal function. So we need the diffusion model should know at which step is EC. Is it close to H0 already, or is it not? Is it close to did it finish the denoising or not? So this thing guides diffusion model, this tool. And so how the training is done? They provide a step-by-step description for training the model. So they first extract the 2D heat maps using together with the estimated 2D pose using a 2D pose detector. Then they compute Z distribution either from a training set or predicted by the context encoder. Then they fit GMM, the Gaussian mixture model, to the indeterminate 3D pose distribution that was generated from the second step. Then based on GMM model, they use the ground truth 3D pose to directly generate n sets of H1 to HK. And so for each HI, we have n sets. Then they extract special temporal context using the context encoder. And then in the end, they minimize the following loss function, which is simply they want to find the difference between the the generated noisy model and the ground truth noisy model. Is it so? They want to minimize this error difference, F2 square. For testing though, they first initialize indeterminate 3D pose distribution and extract spatial temporal context, as can be seen from this picture. So they initialize this. Then they sample n poses from indeterminate 3D pose distribution to recurrently feed them into a diffusion model to denoise and obtain n high quality 3D poses. So let me show n poses here. From this HK, they sample n poses and they feed it to the diffusion model, and they come to H(k) minus 1, they go back again, do the same process, go back, they do the same process again, until they reach H0, when k is equal to 0. Then they have this determinate XYZ pose distribution, H0, and then the final XYZ pose HS. And this final XYZ pose HS is obtained by calculating the mean of n denoised samples here. This n denoised samples. So what model did they choose for diffusion model? They chose very lightweight graph convolution network based architecture modified from an existing architecture from previous paper. And they also use context encoder with the transformer-based network, again borrowed from another work. They did not give a new, they did not propose a new context encoder. And that's the GCN I'm talking about. So it contains several graph convolution layers and attention layers and skip connections and so on. So they did experiments on two datasets, human 3.6M dataset and MPI INF 3DHP. So the number of pose samples set to 5. So this number of pose samples is this N I was talking about. And number of reverse diffusion steps set to 50. So this K is this big K is 50. And they use the existing architecture as a context encoder depending on pose estimation studies. If it is a video based, means we take the context from 2D pose sequence or frame based, where we get just from one image. So here the results in the table 1, we can see two tables. The top table represents the video based results on human 3.6M on detected 2D poses. So they use a existing off-the-shelf 2D pose detector, CPN, and they generate 2D poses with that. And as you can see, the result, it's always better than the previous approaches. And the bottom one is the ones that uses ground truth 2D poses. So they don't use a 2D pose detector, they just use ground truth poses. 2D poses, and as you can see, results are still better. On average, it decreased the error by 4 millimeters. And this table 3 is frame-based results. So in this one, we do not use video. We do not use context encoder for extracting 2D pose sequence information, but we just use one image. And as you can see, it's still better than the previous approaches considerably. And they also did experiment on this MPI and CVPR, and as you can see, the results are much better than previous ones. And they did some ablation study. First of all, they did ablation study for diffusion pipeline. So this baseline A represents a diffusion pipeline that consists of one step only. So the big K is equal to 1. As you can see, the results are not that good. And the baseline B is the stack of diffusion models. This is again not good. But DiffPose is performing better than others. And this table 5 is ablation study for GMM design. So GMM, we choose kernels. They say that using M equal to 5 kernels is enough for saturating to the error rate. So as you can see, the results are not that different when you go from 5 to 9. It's very similar. Then they did the ablation study for the feature context encoder. So just using only the encoder for 3D pose estimation, the results are worse than using their method plus the feature encoder, the context encoder. And this figure shows evaluation of parameters K and N. So N is number of samples K is the diffusion steps. As you can see, it saturates at this point. This number represents MPJPE arrow, so it decreases significantly, but at this point it stops. And we have a table 7 that shows the analysis of speed. So as you can see, the FPS is pretty high, and this DDIM is an approach that can perform the reverse diffusion process in just 5 steps. So if they use this approach, the FPS is much higher than without using this DDIM. And yeah, that's all for me. Thank you for listening.